Hi everyone, this is your struggling CS student, and today let's solve another problem of the day. Let's take a look at today's problem, power grid maintenance 3607. Oh, by the way, uh, yeah, for yesterday's problem, there was no way in hell I was gonna be able to solve that, um, because it's like rated 2600 or something. So yeah, that was quite difficult. I was also busy, had an interview, so yeah, didn't really record the video. As for the weekly problem, it was also very difficult. I tried it like a few days ago, didn't really record it. I just thought of trying the weekly problem. Okay, so enough of that. Let's take a look at today's problem, 3607 power grid maintenance. Okay, it's a 16 to 1700 rated question, so should be doable. You are given an integer C representing C power stations. Okay, each with a unique identifier ID from 1 to C and it's one based indexing. Okay, so these stations are interconnected via n bidirectional cables represented by 2D array connections. Okay, where each element connection of I indicates that there's a connection between station U and station B. Stations that are directly or indirectly connected form a power grid. Okay, initially all stations are online operational. You're given a 2D array queries where for each query is one of the following two types. Okay, so type 1, a maintenance check is requested on station X. If station X is online, it resolves the check by itself. If station X is offline, the check is resolved by the operational station with the smallest ID in the same power grid as X. It resolves the check. If the station X is offline, the check is resolved by the operation. Oh, okay. So if the station is online, you're done. If the station is offline, then in the same power grid, we want the power station with the smallest ID. Okay. So if there's no operational grid that exists, if there's no operational station that exists in the grid with a -1. For query 2, that is station X goes offline, so it becomes non-operational. Return an array of integers representing the results of each query of type 1 and type return an array of integers representing the results of each query of type 1 in the order that they appear. I see. Okay, so there is no result for the query of type 2. So for every query of type 1, we have to return the result of that query. Note the power grid preserves its structure. An online non-operational node remains part of its grid, and taking it offline does not alter connectivity. Okay, I see. And I guess one thing to uh, notice here is that there's actually no types of query that actually turns the station back on. Once the station goes offline, it just becomes non-operational forever, it seems. Unless I missed out some part of the question. Okay, let's take a look. There are 5 power stations, okay, and you have connections from 1 to 2 to 3 to 4 to 5. And the query is 1, type 2, type 1, type 2, type 1, type 2, type 1, etc., etc. There are 3 type 1s, and this is the answer for each of the type 1 queries. So initially, all stations are online and they form a single power grid. Query 1 3. Station 3 is online, so the check is resolved by station 3. Station 2 goes offline, and we want to do a check on station 1. The next closest is station 2, so station 2 is the answer. Then a query turns off, the type 2 query turns off station 2. So then we do a query on station 1 again. Because station 1 is offline, station 2 is also offline. The next uh the next closest is station 3. Hmm. Okay. there are no connections. There are no connections in this case, so each station is its own isolated grid. You query station 1 by itself, that's fine. So you just return 1 itself. You query station 2, no, the type 2 query turns off station 1, and you do a type 1 query again on station 1, and because station 1 is closed or is offline, there are no stations in this grid, so the result is -1. Okay. What comes to mind immediately is to use a heap or like a min heap. So it's basically like priority queue. So we need to for each station we check whether it's online or offline, right? If it's wait, let me do a check real quick. We'll return just the empty list in this case. Let's see for case 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 1. Yeah, let's see for case 1, you know, we query 3 first, but what if we turn 3 off first? So there's a type 2 query, we turn 3 off first. So my expectation for this is it's gonna be station 1, right? So it'll be like 1. Oh, let's see. Yep, it's 1 because we turn 3 off. Then we query the check on station 3 because it's off. 1 is the next one that's online. We turn 1 off and we query 1, right? So the next available is 2. We turn 2 off and we query 2. Now 1, 2, 3 is off, so 4 is the next one available. Okay. So yeah, I think we can use like a dictionary. We can map how should I say, like all we can map all the stations that form a grid, and we can put them in a priority queue. So we can do a check. If the station is offline, no, sorry, if the station is online, it's easy because we can just return the station number itself. But if the station is offline, then what we want is the front of the priority queue for that particular grid, right? In that case, that will be the station ID with the smallest ID. So maybe we can just do like a quick like a quick dry run, I guess. Okay, so suppose we have like 1, 2, 3, 4. This would form like a particular grid. It doesn't even have to be like that. It could be like 1, 2, something like that, right? Then we can have like 5. We can have like 5, 6, maybe 7. I'm not sure. I think this should also be fine. Maybe something like this, right? Make it like as complicated as we can. Actually, I'll venture to say these two cases are the same. The more interesting case would be if there are no connections. So there'll be like let's say 5 and let's say 6. So for when we query this, we want to check, is this let's say all of them are initially online, right? We'll query this. Let's say we do a type 1 query on node 2. Node 2 is online, so we just return node 2 itself. Otherwise, we need to support some sort of like heap deletion, which is fine. We can use like a lazy heap to resolve that, right? So I'll explain what a lazy heap is, but I just want to do a dry run first. So let's say you'll be 3 grids like this. Okay, 3 grids like this. Our heap will point to, we'll have this as the front of the queue. But if we delete this has to be the front of the queue, right? But you can, the front of the heap, or the top of the heap rather. Okay, imagine a case where, okay, we delete this, or we turn it offline. Then when we delete this, our lazy heap has to support lazy deletion. So the next time we check the front of the queue, the answer should be this. That's fine. But do we really need to use a union find data structure? Because like we have to map all the it's a little bit troublesome, I guess. Basically, we have to map all of the nodes to like a connected component, right? In this case, yeah. There are like different ways of doing it. You can build the graph up first, and then you use a DFS, and then you give each node like an ID to its particular connected component. Or you can use like a union find data structure. You know what? Let's do a union find data structure, and let's do lazy heap deletion as well. So just to get some practice in, right? I haven't done union find in a while, so let's do union find. Okay. So if you don't know union find data structure, basically it's well, sometimes they call it DSU as well, or disjoint set union. It's a data structure that can efficiently keep track of disjoint uh, disjoint sets of nodes. So in this case, you can see that this is we will say that this is one of the disjoint sets. This is another, and this is another. So there are three disjoint sets, right? So what the union finds data structure allows you to do is to quickly check if two nodes are connected to each other, right? If two nodes are connected to each other. So you will check if, let's say, you want to check if this and this node is connected, right? So then you would, yeah, the union find data structure allows you, it returns the answer to the question whether two nodes are connected in amortized constant time. So that's really pretty good. Actually, do we really need a union find data structure? Let me drink some water first. I guess we can write the pseudocode out first and see if like union find allows us to solve the code in an elegant manner. If not, maybe we can explore other ways of doing it. Another one would be like doing the DFS thing that I just mentioned. Oh, I see. Wait, let me check the constraints. Uh, oh, okay. 10 to the power of 5, so slot, it's quite a lot. No, no, yeah, DFS would also work. BFS would also work. Okay, let's write the pseudocode out first. See if the union find solution works. I think it works, but let's just see. So we'll say something like union find is equals to union find. We actually have to implement this structure out ourselves later. So that would be uh, C plus 1 maybe, or maybe maybe C. Let's just put in C for now. So we actually need like the number of elements that we want to keep track of in the union find. And we say, okay, for station 1 and station 2, right? So for station A and station B in connections, we would union find dot union A and B. Okay, once they are being combined, then we can say for query in, or we need another separate data structure like a set. So we say if it's turned off is equals to like an empty set, right? Okay, so for query in queries, so we have the type of query. Okay, type is a keyword. Let's see what you say. Okay, for type of the query as well as the station number in queries, right? We would say if station. So if the type of the query is type 1, we want to say also we need the answer output. So answer is equals like the empty list. Is that what they want? That's what they want. We would return answer. Okay, so if answer is equals to 1, answer dot append. No. If station is not in turned off, right? That means the station is turned on. It's easy. We can just append the station itself, right? Otherwise, if, or actually it's just else, so if the station is turned off, we actually have to find the root component of the disjoint set. So union find station, right? From here we get the component ID. Would say maybe like the root is equals to union find.station, and then from there we actually need to have a mapping. Maybe I just call the how should I call it? Component ID to heat map. Component map. Yeah, sure, that's fine. I guess we will have like a default date of lazy heat. So we also actually have to implement this ourselves, or actually I think probably like lambda return a lazy heat, like so. Okay, we have the root, then we say component map of the root. That's how we get the heat here. Then we say dot pick, and we want to append this to our answer. Oh, come on. Append this to answer. Okay, otherwise what we'll do is we'll turn the station off, right? If we turn the station off, turn off dot add the station. We also have to delete this from our priority queue because we can no longer consider this, right? In that case, we have to find the root of the element. We have to also update the heap. So how we will update the heap is we get the component map of the root, then we say dot delete station. Okay, cool. So actually the code is quite clean, using a union find and a lazy heap. So we just do that. Now what we need to do is to actually implement lazy heap. And we also need to implement the union find data structure. So let's implement the union find data structure first. So for the union find data structure, the constructor takes in what are we passing? Yep, the number of elements. So that would be n here. But our mapping is actually it's one base indexing, right? So we just have to be a little bit careful when we do the union find find and union operations. So what we can do is let's do find self dot root is equals to I for I in range of n. So what this code is saying is that every node in the disjoint set, the ID is itself at first, because you can think about it this way. Let me erase this. Actually, oh, that's a bummer. I need dotted lines. So you can imagine, as we are, before we process the connections here, each node, it's grid itself, so we haven't connect the stations yet. So as we do the union operation, that is when we actually connect the two grids together. So we'll color it like this and color it like this, so on and so forth, right? So initially, all of the nodes, before they're connected to one another, it's, well, they are so-called node IDs. It's just itself. But um, as we merge nodes together or union nodes together, that's where we have to update the component ID. Okay. So I hope that I explained that well enough. If you know the union find data structure, you probably might have understood what I said. All my explanation is poor. Yeah. Anyway, so each of the components root ID is itself at first. Then we say self number of components is equals to n. Self dot number of elements is equals to n. Then we have self dot sizes, the size is equals to 1 for I, well, for placeholder range of n. I feel like I'm missing something here. Well, let's just watch it. Well, what we need to do is we need to implement the union method. So AD, like so. We also need to implement the define method. So let's implement the find method first. Okay, so for the find method, if the node's parent is itself, we're done. So if self dot root of A is equals itself, then that's the root ID. Well, we can just return, that's what we return. We can just return A itself. Okay, otherwise, the self dot root of A is equals to self dot find of its parent. Return self dot root. So this is where we do union find path compression. It's a little bit hard to explain. I'm not gonna attempt to teach union find path compression in this video. There are tons of videos out there that probably do a better job than I do. But essentially, what it does is, suppose you have a node that goes like this, like this. Now somehow you have this type of construction of the disjoint set union, okay? And you say, okay, I want to check if this guy's parent is equals to itself. Okay, so this guy's parent is not equal to itself. So this guy will point to this guy will point to this guy, this guy will point to this guy, and this guy will point to itself. So this guy is this guy's the root in this case. So because this guy's parent is not equal to itself, we would traverse up to the root, and actually we'll update all the links along the way. Actually, for this guy's parent pointer is not updated, but we would update this to point to this, and we update this to point to this. So that's where the recursion finds A, and then we update this one when we roll back the recursion. Then we return back the parent. Return that back the parent. So yeah, probably a little bit hard to get wrap your head around, but when I first learned it, it also took some time. Okay, so this is how we will implement union find with path compression. Then from here, we want to union two nodes together. Okay, two nodes together, or two components together. So we say a root is equals to self dot phi of A, and B root is equals to self dot phi of B. Then we say if A root is equals to B root, we're done, because they are already part of the same component. Otherwise, we actually want to choose the node with the larger height, I think. So let me see. Let me just do a quick run. So let's say you have like a tree like this, and a tree like this, two components, and you're joining two nodes together. Yeah, you would choose the one with the larger height. That's what the size here is keeping track of. This is what it's keeping track of. Yeah. I feel like I'm missing something here. I'm missing keeping track of one more thing that I don't remember. Well, if we need it, we'll need it. I'll try to recall it. So, you never want to extend the height if possible. So, in this case, joining it like this is better, I think. Wait, hold on a second. So if let's say, if you choose this as the root, right? If you choose the one with the lesser height, and you choose this as the root, let's say this is one of the root, this is another root. You extend it like this. You extend the height of the tree. That's what we want to avoid. If we connect it the other way around, and this guy points to this guy, then the height of the tree remains it's constrained to the larger one. Okay. So if self dot sizes, keep mistyping. Self dot sizes of a root is larger than self dot sizes of is it called the height instead? B root. Now if the other way around, else, so here is self dot num components dot no minus equals 1. Okay, this is B root instead. This is A root. Actually, do I do it the other way around? Yeah, I think I do it the other way around. So if this is lesser, A root, B root, and otherwise what happens if they're the same? Ah, okay, I remember now. So from here, I think the one thing I need to keep track of is their rank. Yep, it's actually their rank. So the rank here would be the height that I was talking about just now, and the size is actually the number of elements in the a particular component. That's based on its root ID. Okay, so actually this is rank instead. This is rank. So we choose the one with the lower rank. No, we choose the one with the higher rank. Okay, so from here we would say self.root of A root is equals to B root. Then we say self.sizes. I don't know. Self.sizes of B root that is gonna add the self.sizes of A root, and self.sizes of A root is equals to 0. That's because once the smaller component, let's say this is A root, right, and this is B root. So A points to B. When we query the size for this particular disjoint set union, it should really return the size of this one. So this one should add the size of this one. Okay, and then we need to set it to 0. Then now we just need to switch it. So this will be B root, and then this is A root. Then otherwise, if they're the same, we can choose B root, and then we say self.rank of B root plus equals 1. So A root points to B root. B root gets all of its size. We set the size to 0, and then B root rank increased by 1, and then we decrement the number of components. Okay, cool. Okay. Okay, finally that is done, at least for the union find. Now we need to implement the lazy heap. Hopefully it's not too bad. Okay, so actually lazy heap is not too bad, yeah. So underscore init self, and I think that's it. So self.heap is equals to the empty array. Self.deleted is equals to a counter to keep track of the number of elements that has been deleted from the heap in a lazy fashion. Okay, so what operations do we need? Actually, I realized we also have to connect. The union find to the lazy heap. Okay, so let's see how we are doing it right now. Yes, that's fine. So we would say for I a range of C. I guess here, because there's one base index, what we can do is we can do -1, -1. I'm taking so long for this question. I feel like it shouldn't have taken so long, but yeah. Anyway, okay, now for I in range of C, we do union find dot find the root, right? So let's say this is station. This is station, we need a component map here. Once we find the root, then let's say this is the root, is equals to this, component map of root dot push station. Okay. Yep. Okay, back to our lazy heap. We need push. Do we need pop? No, we just need the pick and delete and push. So we have that push self of x. This is easy. Self dot heap dot push. Nope, it's heap push of self dot heap of x. Then we have the pick of self. Okay. Yeah. Then we have delete. Okay, let's put delete at top here. Then for delete of self of x. Okay, self dot deleted of x plus equals 1. Yep, so the lazy deletion will actually happen here, or the lazy update. So we say wow, self dot heap and self dot heap of 0 in self dot deleted. So what we will say is the element at the top is already been deleted, so we have to remove it. So heap pop of self dot heap. This is x self dot deleted of x minus equals 1, and then we have to do a check. If this is equals to 0, we delete it. Okay, so if self dot heap, or rather if not self dot heap, we will raise an error or an exception rather. We say pop from empty heap. Otherwise, actually this is pick from empty heap. Otherwise, we can return self.heap of 0. So if I have done everything properly, the code should work. Let's see. Let's give it a dry run. Of course, there's no sizes because it's called size. All right. Let's do a quick fix here. Pick from empty heap. Oh no. So the station has been turned off. Okay, that's cool. So in that case, we will actually return -1. Right. Yeah. When we turn off the station and we don't find an operational station that exists in that grid, we have to return -1. So I guess instead of like raising an exception here, and trying to catch it and returning -1, maybe that code is a little bit better. Yeah, let's do that. Let's do that. Try. Then we'd say if we catch an error, no, this is accept. Then we say answer.append -1. No, 0. I see, I see. Because we're doing one base indexing, now everything is wrong. Uh, please tell me I'm just off by one. Yep, I'm just off by one. Oh, okay, that's great news actually. So every time we append the answer, because now it's zero based, you know, because of this change, what we can do is when we append the answer, we just do a plus one. We do a plus one. Okay, some minor tweaks here and there, and yeah, there were some minor bugs that got through because of like the index, the switch between like one base indexing and zero base indexing, and it passed the sample test cases. Am I confident? I feel like conceptually my answer is correct, but like if it passed in the first try, I'm not sure. Let's give it a try again. Okay, that's good. Let's YOLO submit. And it's got accepted. Nice. So I got my practice of union find in as well as lazy heap. That's good for me, I guess. And hopefully you learn something as well. Next, analyze the time and space complexity of this solution. The time complexity and the space complexity of constructing a union find is actually OC, or linear with respect to the input, right? So OC, where C is the number of power stations. So that's the time and space complexity. Both is OC. Now the component map here, well, we are again, it's possible that each station is a grid unto itself. In that case, the space complexity is ON, OC, and the time complexity is also OC. Okay, so the union find operation, it actually takes amortized constant time. But if you want to be very, very exact, actually it's not amortized constant time, sorry, it's just straight up constant time, because the growth of the time complexity with respect to the input is so small that it's considered constant time. But if you want to be very precise, the time complexity for the unified method is actually with path compression is actually the inverse Ackermann function, if I remember, if memory serves. Okay, and actually this is the time complexity of this code is not OC, it's actually C log C, I guess. Yeah, because we do a OC loop, and this push function actually takes log C of time. If let's say every station is connected in the same power grid, it's connected in the same power grid. Okay, then from here, what's the time complexity here? We again use a set data structure to keep track of the power station that are turned off. Okay, we don't count the output array for this space complexity, because that is what we need to return. So usually you wouldn't count it as part of your space complexity and analysis. So what's the runtime for this loop? Well, for this loop, it's O queries, and here we do a check. This is we just check if the station is turned off or not. This is O1 check. Otherwise, this is a constant time check. Otherwise, if we are doing the pick operation, this is a log C runtime. So this is like query times log C in the worst case. Here, same thing. When we add, this is constant time. The delete operation is also constant time. It's just constant time. And then we return the answer. So maybe I can just write it out. So the really at the top, the time complexity is OC plus C log C. C log C plus query. I'll call it Q log C. Yeah, C log C plus Q log C. Right, this is a C part. C log C plus Q log C. Okay. Then the space complexity is O of what? O of C plus, well, just OC, right? Because here, we do C space we do up to C space as well, possibly, and do up to C space. So 3 linear data structures with respect to the input. So this is the time and space complexity. I'm just going to do a quick submit again to record my submission for the time and space complexity. Cool. Let me reset the code. You can see this, my first solve of this question. Let's take a look at the tutorial. Okay, cool. So actually, the editor also did union find. But what is this reverse processing query? That's interesting. Yep, path compression optimization. Yep. Use the root node to handle. Yep. Hmm. Hmm. Cool. So this is the path compression. This is the union operation, I think. Yeah. This interesting. The union operation is so simple compared to my uh Jesus. Hmm. I see. I see. Okay. Theirs might not be the most optimal, but the next time you call path compression, it makes it optimal. Hmm. Okay. So instead of avoiding the one base indexing, sorry, instead of transforming one base indexing to zero base indexing and then transforming back zero base indexing to one base indexing, they just embrace the one base indexing. Okay, cool. Mm-hmm. Okay, so they pre-process queries here. I feel like my code is clearer, man. I don't know. This part looks a little bit complicated, I guess. I see. This is where they do the inverse Ackermann function. Yep. So memory did serve me correctly. Plus priority queue. Yeah, that's what I thought. I didn't do BFS or DFS. I do union find plus priority queue with lazy heap deletion. That's also fine. Yep. Yep. Yeah, you have to implement a custom lazy heap. Yeah, see, lazy heap deletion. Where deletion is handled uniformly. Yep. Mm. Which is what I did. My approach is more akin to approach 2. Oh, they even have a separate data structure. Okay, cool. They have a graph. Come on, man. This is okay. Okay. Bro, really? Come on, man. Just put it all in the main function. Ah, okay. They did the lazy deletion here. Mm. Yeah. Okay. That I'm not sure. Yeah, I would. I agree. I agree. Maybe I want to take a look at this again. The reverse order thingy. Oh. Hmm. Actually, the problem itself is not like super complicated. The hard part of this problem is implementation problem, right? Because and also like understanding of different, at least for my solution, two different data structures. You have to understand union find, or sometimes called, or other times called disjoint set union. You also have to understand lazy heap deletion. Um, yeah, and then from there, you know, you might ask, what's the advantage here of like using, what's the advantage between like my approach versus like approach one, which is using union find plus reverse processing query? Well, the advantage of my solution is actually we can process the queries in an off no, no sorry in an online manner. Well, what does that mean? That means that once we have constructed the union find data structure as well as the lazy heap, okay, we can process the queries as they come in. We do not need to know the queries ahead of time. Whereas you compare the approach to approach one in the union find plus reverse query processing, approach one assumes that it knows what the future queries are, which in the real life setting, you may or may not have that information. And most of the time, to be honest, you won't have that information, right? If you don't have that information, well, then you can only process it in an online manner as they come in. So that's the advantage that my solution has over the solution the editorial is showing. But let's take a look at the reverse processing query part because I didn't really understand that as well. Okay, let's see. This is where they do the reverse processing. So anytime a station is taken offline, it just marks it as offline forever. Yeah, we make that same observation once. A station is turned off, it's never turned on again, and we pre-process the offline count. Okay. From here, get the routes, and if the route is not in minimum online station, if it's online, so if the station is equal to -1. Okay, I'm not sure if I understand this code, man. Okay, I'm not really sure if I understand the code, unfortunately. Okay, but anyways, yeah, I guess you can also like consider processing all the queries um, first, because in LeetCode, yeah, that's an option that you can do. Process it offline first and derive some sort of insight to abuse from there. But otherwise, this is my code. I'm just going to show you one more time, like so. Okay, this is the union find code, like so. And this is the lazy heap code. All right, that's all from me. Thanks for watching and have a great one.